Hello and welcome back to Odds. In this video, we're going to be going over time of flight, its derivation, and which scenarios it works in, as well as some practice problems. Because it doesn't work in all scenarios, at least this formula doesn't. You can find the time of flight, of course, but it takes a bit more work if you don't have the formula. So, let's get started. Imagine you have a projectile that is started at the same height and lands at the same height. Okay, so like this. It starts at y is equal to 0, y initial is equal to 0, and it ends at yf is equal to 0. So in this case, if we were to use this equation, right? If we were to use yf is equal to y initial plus v0 or v initial y t minus 1/2 gt squared, which is one of the projectile motion vertical equations, right? Which you can check out on my other video. Then, is there a way to simplify this delta y? So we subtract yi from both sides. We get delta y is equal to this business, viyt minus 1/2 gt squared. If we end and start at the same point, what do we know? I mean, in this case, it's 0 and 0. But imagine we started from a table. Okay, imagine we started from a table. We started at 2. And then we landed on another table at 2. In that scenario also would work. What would work? If you do yf minus yi, what do you get? You get 0, right? That's the time of flight because that's how long it takes to get there. That's your yf position. That's your change in y. Your change in y is nothing because you end up at the same point you started. Okay? So that's going to be equal to this thing. And we can factor this out, right? We can go t vi y initial minus 1/2 gt. So this is giving us two solutions. T is one solution when t is equal to 0. And there's another solution when this stuff is equal to 0. But first, let me look at the t solution. When t is equal to 0, that means it started at exactly that point, right? We don't have a range. We don't have a time of flight. Why is that? Because if we start out at the same point we finish, then the change between yf and yi will be 0, right? So we could have a yf that's placed right here. Exactly the same point as yi. Then yf minus yi is still going to be 0, even though it's wrong because you can't have a yf that's point. The actual yf minus yi should be this one because that's the range, right? How far did it go? What's the time of flight? Where did it land? How many seconds did it take for that? So this is in the case that yf and yr are the same value, which they are, but they start at the same point, which they don't, right? We can see clearly that they end at different points. So t equals 0 is not a solution. Because, I mean, even if you look at it graphically, you can see that at t equals 0, we don't have the time of flight, right? What do we have? We just have the same point. The time of flight is this thing minus this thing. That's what we want to find. This entire second duration. So that means it's probably the other solution. So I can set this equal to 0. viy minus 1/2 gt is equal to 0. So I could subtract from vi on both sides, viy, and then divide that by 1/2 g. So it becomes 2 viy over g. So if it's a bit confusing what I just did there, I subtracted from viy, so it became negative viy is equal to negative 1/2 gt. And then I just multiplied by negative 2 to clear this. 2 viy over g is equal to t. Okay? And then this t we denote as capital T because this isn't just regular time, right? It's the total time of flight. So we're just writing it different. But you can see how it's basically just regular t. So that's where you get the formula from. You see, it's pretty neat. And then you don't need to derive this formula, right? If you plug in the right values into this equation, you can still get the same formula. If you plug in yf, yi, you're going to get 0 on this side, and then you can factor this, and then you can find it. But, I thought, why not? If I could just show you the formula. Although this does only work in the scenario where yf and yi are the same. But don't they always have to be same? What do you mean by, how can you have a time of flight if they don't end up at the same spot? Well, you could have something like this, right? Suppose you were up in the sky at a mountain, and then you threw the ball. So you have an initial vertical y, right? You already have an initial yi. Your yf is going to be different, though, because you hit the spot. So yf minus yi in this case is not 0. So for this case, you can still use this regular equation, but it does take you a tad bit more time, right? Because yf minus yi won't be equal to 0, so then you can factor this out to get equal to 0. Otherwise, this one is good, or you could just keep plugging in. Also in the scenario where you start initially here, but you land on something else. And you have a different yf than a yi. Okay? All right. So now let's go over, an example practice problem together. Launch at 28 meters per second. As always with projectile motion, draw the graphs. My velocity initial is, so if I was to draw a velocity vector, my velocity initial would be 28 meters per second. At 40 degrees from level ground. So remember, I was showing you a problem where it said 40 degrees from vertical. This time we don't need to worry about that. It's a tad bit more simple. Just simple 40 degrees here. So then I want to find the time of flight of this projectile. So I didn't tell you the fact that it has to be yf and yi are the same, but I'm just going to tell you now, okay? Let's just say that it ends at the same point. Let me just give you that as one of the requirements. So then you can use the formula. You don't need to use the whole, the y position acceleration equation for vertical projectile motion. So here, what do? I remember that my period or my time of flight was 2 VI y initial over g. So VYI initial is what? First, over here it's 40 degrees, right? So we know, how do we find Vy from just a regular vector with magnitude something? We multiply that by the sine of this angle. So VIY is going to be 28 meters per second times sine of 30 degrees. 40 degrees. So yeah, you don't want to mix up your angles like I almost did there. And then if you put in your calculator, which I'm going to do right now, so 28 times sine of 40, make sure you're in degree mode, gives you approximately 17.998, which you could round up to 18 meters per second. Okay, so t is equal to 218 meters per second over what? G, which is 9.81 meter per second squared. So t is equal to 36 meter per second divided by 9.81 meter per second squared. So the meter per second and the meter per second cancel out, but this 1 second remains, right? Because this is basically second squared over m. So one of the seconds still remains. So let me erase that. And your answer is going to be 36 divided by 9.81 seconds, which is approximately 3.67 seconds. That's how you find the time of flight. If it's more intuitive for you to use just this equation, yf is equal to yi plus viyt minus 1/2 gt squared, you can just use this equation, okay? This is just a formula that works under certain conditions. And I just want to make it known to you because it can help you a lot at times. So let's go over some problems together. As always, more comprehensive problems are going to be on odds, and more realistic and harder problems as well. Because my goal is to prepare you for everything that could be on the test, and I'm trying to do exactly that. That'll be on oddslearning.com and the later videos. This is just to make sure you know the basic content, which I just taught right now. Okay, so first, give it a try on your own, and then I'll walk you through it. I'm assuming you did it, okay? Standard time of flight. A projectile launches at 30 meters per second, 45 degrees from level ground. So, 45 degrees from level ground. And initial velocity vector is 30 meters per second. Find the total time of flight t. This isn't per se a tricky question. It's pretty straightforward, right? We know t is equal to 2vy initial over g. What is vyi initial? Well, that's just going to be v times sine of theta, right? Or sorry, v initial times sine of theta. Or in other words, 30 meters per second times sine of 45 degrees. So you could do this. You know, sine of 45 is root 2 over 2. So this is going to give you 15 root 2 meter per second. Okay? Now, time, or time of flight, is 2 times this. So 30 root 2 meter per second divided by g, 9.81 meter per second squared. So if you plug this in, and you're going to get around 4.32 seconds. Pretty neat, right? And yeah, obviously you could have also tried to solve this using the other equation, right? The full velocity time equation, or the full acceleration position equation, which I just showed you. But this is, it's a bit more concise, right, for now. So let's just use that. Although that one is the main one, so I would like for you to remember that one as well. Now, let's try working backward to the angle. So we're given the time of flight, but what do we want to do? We want to go backward to the angle itself. So t is equal to 2.5 seconds. Speed is 20 meters per second from level ground. Find vyi, then the launch angle theta. Okay. So always draw your graphs with kinematics. It gets very complicated very soon if you don't. I know that this value over here is 2.5 seconds because that's the time of flight, right? That's where the y ends back down. My speed is 20 meters per second, which means 20 meters per second from level ground, okay, which I'll show you later what it means. Find vyi initial, then the launch angle theta. Okay, so I look at this, I look at my formula. T is equal to 2 vyi initial over g. Now, I know that t, which is 2.5 seconds, is equal to 2 vyi initial over 9.81 meter per second squared. So I try to find out this, right? So what am I going to do? First, let me get some more real estate. I multiply this by 9.81. 9.81 times 2.5. Okay, then I divide that by 2. I get approximately 20, so vyi is approximately 12.2625 meter per second. What am I given? I'm given that the speed is 20 meters per second. Okay, so that's the initial velocity vector over here. The speed is just the magnitude of this velocity vector. So we know that this is velocity y initial. So it's going to be this vector, or v, is equal to vyi. So I'm going to color code it so you can see which one is the magnitude of the vector and then which one is not. And then we know that this is going to be, so I should have probably written it on this side, but sine of theta, because vyi initial is vi initial times sine of theta. V initial is, we don't know that, or we know what y initial is, but we don't know what initial v is. But you might think that, but look at the question again. What is v initial? That's just the magnitude or how fast you're going. No direction, just how fast you're going. The vector might have a direction, but think about how fast you're going. Well, you're going at 20 meters per second, right? So sine of theta is times 20 meters per second is equal to 12.2625 meters per second. You divide both sides by 20 meters per second. So you'll get, if you plug this in your calculator, and then arc sine of that, you should get around 37.815. So I'm going to round up to 2 degrees from horizontal. Pretty neat, right? So I would probably box in both these answers because they asked for both of them, right? Yeah. Other than that, it was pretty chill of a problem. Although, of course, this v initial could be confused with speed because speed and velocity are not the same, right? But always remember that speed is just the magnitude of the velocity vector, no direction. And in this case, they gave it just the magnitude, which is what we wanted.